Now, we've talked about polar and nonpolar compounds, but it turns out we can have molecules that have both polar and nonpolar parts, and these are called amphipathic compounds. So these are molecules that have both polar and nonpolar parts. And because of this, they can do some really interesting chemistry, right? So when we look at these molecules, there's a few things to keep kind of in mind. Generally, these molecules are nonpolar. The nonpolar part is something like a long hydrocarbon tail. Now, a hydrocarbon tail, when we talk about that, that is just a molecule that contains carbon and hydrogen, right? So hydrocarbon, hydrogen, carbon, carbon, that's what that means. So this here, right, is that nonpolar part. Then the polar part that's right here is a lot of times it's referred to as an ionic head. It contains a carboxylate. Now, a carboxylate, when we talk about this, is just a combination of atoms. And that combination of atoms can look like this, right? Where we have a carbon that's double bonded to an oxygen with another oxygen with a negative charge. Now, these carboxylates are a little tricky because they can be shown as like this, or they can also be shown like that. Rare, you'll see them like this. Most often, you'll see them either with the double bond shown, or it'll be this condensed version where the double bond isn't shown at all. So these are carboxylates. And the important part here is that they have this negative charge. That negative charge is one of the contributing factors that makes them polar. So this is called a ball and stick model. It shows you all of the atoms where oxygen is in red here and carbon is in black. And then the hydrogens are kind of these gray molecules or these gray atoms. But most often what we see will be a cartoon representation. If you've taken biology, you've probably seen this in some lipid bilayers where the negative part here that's really polar is shown as a circle. And then the nonpolar part is shown here. And again, this is referred to as a tail, and that's referred to as a head. So this is the cartoon version that we'll look at. So let's put a little words to this. The nonpolar tails are hydrophobic. And hydrophobic just means water fearing. So hydro means water, phobic means fearing, and that means they'll be excluded from water. So they're pushed away from water. They have those London dispersion forces. That's the only intermolecular force they have. The ionic heads are hydrophilic. And that means they're water loving. When we talk about things that are ionic here, it's not that metal and non-metal definition anymore. It's the fact that there's a charge there. And through that charge, they can interact with water through ion dipole interaction. So those are the intermolecular forces they use there. So these amphipathic compounds are really important when we talk about soaps. So let's come over here and look at soaps. So when we talk about soaps and dirt and we think about what soaps do, right? So soaps are going to come in and soaps basically, right, remove oil and dirt, okay? And these things by and far we classify as being nonpolar. But soaps function in a polar environment, which is water, right? So soaps are going to function in this polar environment, which is water. So, right, how does this work? Okay. Well, when we think about these molecules where they have this polar area and this non-polar area, they self-assemble into these structures which are called micelles. And when they self-assemble into these structures which are called micelles, these are basically like large spheres. And you can see kind of there are multiple molecules of these phospholipids that go back through here, right? And so when we look at this, what we find is that we have the nonpolar parts that all assemble in the middle, right? Because likes dissolve likes, or they interact with each other. So all those nonpolar tails are together. And then all of the polar heads are on the outside so that they can interact with water. And since oil and dirt are nonpolar, oil and dirt are going to go to the center there and then can be washed away when the micelle is washed away. Okay, so that's in a nutshell how soap functions. So let's put some words to that and talk about this in a little bit more detail. So the tails associate with each other and they create a core of a spherical structure, and that spherical structure is called a micelle. Okay, the polar heads form the shell of the micelle. Okay, and micelles form because the ion dipole and hydrogen bond attractions between water molecules and the ionic heads are stronger than and preferred to the water interactions with the hydrophobic tails. So again, we only have London forces here, but on the outside here, we'll have ion dipole interactions and we'll have hydrogen bonding, right? And so those are the intermolecular force interactions that we have there. When we talk about water molecule, when we talk about soap molecules and what these molecules look like, these come from fats. So when we have not talked about chemical reactions yet, we are going to do that in the next module, but it's still really helpful for us to look at the chemical reaction for how we make soap. So when we look at a chemical reaction, we have reactants here, we have products here. They are separated by this arrow. When we look at this, right, this is a triglyceride. Tri just means three. We have 3 fatty acid molecules that are attached via a glycerol backbone right here. These react with a base. So you take some sort of fat, you mix in something that's really, really basic. Again, we have not talked about this. We will talk about bases when we get to our acid-base chapter or module. But the thing that happens is the glycerol here breaks off and you're left with these carboxylate ions. So we see that C double bond O with an oxygen with a negative charge here. Now you see this R, and if you look at the periodic table, you're not going to see an R on the periodic table. That R there just means the rest of the molecule. And so when we talk about that R being the rest of the molecule, right? For us, it's just carbons and hydrogens. It's the hydrocarbon tail there, okay? So now we have soap, right, which is this carboxylate here. Now it's got a negative charge. You're going to see sodium that's associated with this soap, but in water, it breaks off and just floats away, okay? And so that's how these can form the micelles. Now, amphipathic compounds like soaps are called emulsifiers because they allow nonpolar and polar compounds to be suspended in the same mixture. Okay, so we're still putting some words to what we said on the last slide based on the golden rule. Greasy dirt is not soluble in water. When soap and oily dirt are mixed with water, the hydrocarbon chains are attracted to the greasy dirt and to each other by London dispersion forces, right? So they cluster together, forming those micelles. In the micelles, the dirt is buried down in the center of the sphere with the long molecules pointing outwards. The carboxylate groups end up on the surface, giving the micelle a negatively charged surface. Because they are negatively charged, soap micelles repel each other and remain dispersed in the water. And when you wash the soap away, right, the soap leaves and it takes the dirt with it. And that is how soap works. Now, soap is a good cleanser because it acts as both a surfactant and an emulsifier. And I want us to have some definitions of these. A surfactant adsorbs. And adsorbs means it makes a connection between a polar molecule, which is water, and a non-polar surface, which is oil. Now, an emulsifier is a surfactant capable of causing two immiscible liquids to mix. Now, immiscible just means they will not mix, and that emulsifier comes along and is a helper and helps them mix. So, soap, right, works as an emulsifier by forming those micelles. Those spheres that suspend the nonpolar dirt in the water so they can be washed away. Now, so that's soap. That's how soap works. A large portion of the cosmetic industry is interested in removing oil and dirt from skin, right? That's the whole basis for soap, for shampoo, for detergent, for all of those things, okay? But just as important, a large part of the industry is interested in adding oil to skin, okay? And that's where we get into moisturizers and lotions, okay? So let's talk about those two. Now, to set this up, we really need to talk about skin a little bit, okay? Skin is our largest organ. It covers and protects the human body. It regulates both the body's temperature and the penetration of sunlight, okay? Now, there are 4 layers of tissue that we are going to talk about, and we're going to start kind of at the bottom here. So this is an image of skin. It's from Britannica, and these don't exactly match up with what I'm going to talk to you about. So we're going to have to add a little bit here. So there are 4 layers. That just shows 3 layers. The fat here, that is also known as subcutaneous tissue. Okay, so that's that fat layer that's on the bottom there. So subcutaneous tissue is just the underlying fatty layer, and that's shown with all of those kind of yellow cells there. Now, a few things when we look at this, you are going to see that there are some blood vessels that go through that layer. So we see blood vessels there, shown in both red and blue. We see nerves. Nerves are kind of this darker yellow or orange. Okay. We see oil glands here, right? And we're going to talk a little bit about those oil glands. We also see sweat glands. They're shown here. Okay. And then we see pores on the surface. So sweat comes out of your pores. Oil also comes out of your pores. And then we see the hair follicles here. Okay, so we have hair and glands and all of those things. Okay. The next part that we're going to talk about is right here. This is the dermis. This is just the layer where the nerves, hair follicles, blood vessels, and sweat glands are found. Okay. Now, and something to point out here. We have sebaceous glands. that are located here, and these secrete sebum. Now, this is just an oily substance that coats, lubricates, and softens the skin. Okay. Now, the dermis also makes up the bulk of the skin. Right? And it's composed of a lot of fibers, mainly collagen. Right? Now, collagen is a structural protein. And basically, it just looks like a fiber. Okay. The other thing that is in there as well with collagen are glycosamine glycans. Okay. And that's the structure of them there, the chemical structure of them there. Now, with these guys here, right, this is pretty important when we talk about lotions because this is what is capable of holding a large amount of water. Right? And so what that means is that it helps with skin hydration, volume, and elasticity. Right? So this molecule itself is very hydrophilic, right? That means it's water loving. And so it's going to hold on to that water and help the skin kind of have that plump, healthy look that we think about. It also, right, when we talk about elasticity, right, these are elastic fibers that keep the skin taut, right, and restores it after it's been stretched. And so that's why you wouldn't have wrinkles, right? So if you have wrinkles, your skin's not restored after it's stretched, okay? Now, let's talk about the other two layers, which we've got the epidermis, right? Which when we talk about the epidermis, there is another part that's important, and that's the stratum corneum. And that stratum corneum is this piece right here. Okay. So the epidermis is just the outer layer of skin that contains the stratum corneum. It also contains the cells that provide skin color. Okay. Now, the stratum corneum is what's found on the very, very top. These are a layer of dead skin cells that are continuously shed. Okay. This layer mostly contains keratin, right? Which has a moisture content of about 10%. Okay, and that's pretty important. Below 10%, you have dry skin, right? And above 10%, harmful microorganisms can grow. Now, when we talk about these harmful microorganisms, it's basically worth mentioning we are not alone, right? We have lots and lots of bacteria that live on our skin, okay? So the most common species of bacteria that we find are the 4 that are listed here, okay? So, right, if you have an unbalanced microbiome, right, if that moisture level isn't right, it can be linked to a lot of skin conditions like eczema, dandruff, acne, or dermatitis. And these are, these are really annoying conditions. Now, factors that can affect this microbiome include pH changes, right? And we're going to talk about pH when we get to our acid and base chapter. But any changes that you have in the acidity values on your skin can change this microbiome. Sebum content. So the oil that's produced can change that. Hydration. Lifestyle. Barrier function. Right? Climate. So if you live in a drier climate versus a more humid climate. Gender. Age. And ethnicity. So all of these can affect how dry or oily your skin is, and then can affect what is living on your skin. Okay. Now, helping keep this healthy balance in check is one of the most important functions that skincare can deliver. And it's really an interesting new area of research for cosmetic scientists. And so one of the things that you're going to see pop up quite a bit are skincare with prebiotic ingredients, okay? Now, if we're talking prebiotic ingredients, what we're talking about here is these act as a food source for the bacteria on your skin. And have been shown to have a moderate effect on the population. Balance. Now, it's helpful here, I think, to define prebiotic versus probiotic. Probiotics are live bacteria. So when you have somebody that's like, oh, I'm taking probiotics, right? That's live bacteria. A lot of times we're actually taking prebiotics, which is food for the bacteria, right? And probiotics don't show up in cosmetics quite as much because it's just not practical for that finished formulation that needs to be safe and stable for years, right? So we don't see those as often, but it's nice to kind of talk about the differences there. So we have cosmetics, we have skin. Maybe the burning question in your heart is, hey, Dr. Pierce, do cosmetics into the skin? And the answer is most of the time no, but sometimes yes, right? Which is really annoying. So cosmetic products do most of their work on the surface of the skin, okay? So here's our skin. We've got the epidermis, the dermis. We have these cells. In between these cells, we have fatty acids. They're kind of like the mortar. So if you think about the cells as bricks, this would be the mortar, right? And I actually got this from a medicine website, right? Which is all the ways medicine enters the skin. And it can go intracellularly, where it moves between the cells. It can go transcellularly, where it goes through the cells. It can go transglandularly, where it goes through the glands, right? And then it can go through the follicles or the hair follicles. Moisturization, right, just by definition, right, it's going to work on the surface of the skin, right? So it's most effective on the stratum corneum. Sorry, I got a little wild there, right? And that just slows the rate at which cells dehydrate and shed. That's basically all we're doing. And it plumps the surface and maintains the healthy appearance of that topmost layer of skin. Now, that skin, the whole purpose of skin is to act as a barrier, but certain molecules do have the ability to travel through the stratum corneum and epidermis. A really good example of ones that can travel, and it's not it's classified as a drug, but think about a transdermal drug patch. So I think a lot about like nicotine patches, right? Those chemical compounds can reach the bloodstream, and they do travel from the skin to the bloodstream. Generally, though, with cosmetics, you see it mostly on the surface. There are some exceptions. Retinoids can penetrate the skin. Right? And the idea here is that a cosmetic stays generally on the surface of the skin. When you start to penetrate the skin, you get into drug territory, right? So that's quite iffy when we start to talk about that, particularly when people get into retinoids and bringing about cosmetic changes with the skin. Sometimes those are classified instead as drugs. We will talk more about retinoids towards the end of the class, but it's just helpful to mention it here because they will come up. Now, so we're talking about things coming into the skin. Another concern about skin is that water also leaves the skin, right? Which results in that dry skin that we need to moisturize. So let's talk about moisturizers and what they are. Moisturizers are any substance that replaces lost water from the skin, right? Or, right, retains moisture within the skin by forming a waterproof barrier. And the other thing that a moisturizer will do is soften the skin. Okay. Now, moisturizers are stable mixtures. They're composed of water, an emollient, an emulsifying agent, a humectant, preservatives, thickeners, and most of the time, pH adjusters. And we're going to talk about all of those, and we're going to define all of those later in the screencast. In general, there are two types of moisturizers. There are creams and lotions. Creams are more like a solid. Lotions are more like a liquid. And something that has kind of come on when we talk about moisturizers, has kind of come on the horizon recently have been oils, right? So you can see things like shower oils that are supposed to moisturize. So sometimes we'll see oils, but for us, we're really going to talk about creams and lotions, right? So creams are like a solid. Think like body butter, right, is a cream. Lotions are more like a liquid. Now, here's the deal when we talk about these. Moisturizers help with dry skin basically just because they supply a little bit of water to the skin and contain a greasy substance that holds it in, right? So these work because they supply water to the skin and contain a greasy substance to hold it in. In fact, if greasiness wasn't such a problem, we would probably all go back to using the solution for dry skin that our grandparents use, just white petroleum, which is Vaseline. But that Vaseline sort of fell out of favor because it keeps your skin feeling like greasy or sticky or tacky, and people were annoyed by that, right? And so that proliferation of moisturizers is just searching for this mix of ingredients that holds in water like petroleum but feels nicer than the skin, right? And so that's kind of this quest for the best moisturizer. And a lot of that just has to do with your personal preference, okay? Most lotions their main component is water, and you have to be careful when the main component is water, because where water is, bacteria loves to grow. So you have to have something that can keep bacteria and fungus from growing as well. Now, let's talk about how lotions are classified. So lotions are broadly classified as colloids. Colloids are just a mixture of particles dispersed throughout a solvent like medium. Okay, so we've got two phases here. We have a dispersed phase, and these are just the particles that are distributed through the colloid, right? And they're shown in green here, but I did it in blue to kind of show you where those are, okay? So that's the dispersed phase. Those are the itty bitty particles that are spread out through the continuous phase. The continuous phase, right, which is shown there in kind of that yellowy orange, is the solvent like medium of the colloid, right? So that's functioning all in here, right, as the solvent, okay? So the continuous phase is like the solvent. The dispersed phase is the little bitty particles that are through there. Now, those two phases can exist as a gas, liquid, or solid, okay? I mean, we find colloids in all sorts of parts of our lives, right? Colloids tend to be classified based on the states of the two phases. Because we are mostly interested in moisturizers, right? Those two phases are liquid-liquid colloids, and those are known as emulsions. Okay, so that's what we're interested in. So what is an emulsion? Emulsion is just a mixture of two immiscible liquids So immiscible means they do not mix, that are forced to mix by the addition of an emulsifying agent and agitation, which just means mixing up. Okay. A really good example are most of what we're going to see are oil and water, right? These are the two immiscible liquids. Moisturizers are either emulsions where we have an oil dispersed in a water. Okay, so here's an example of an oil dispersed in a water where the continuous phase is water and the dispersed phase is oil, right? You can see those. So oil and water, and these are referred to as OW, oil and water, right? Or it can be water in oil, WO, where we have water are the little droplets here, right, that you see, and it's dispersed throughout an oil, okay? Here, with an oil and water, how these work is that water will evaporate to leave a protective oil layer behind. Okay, that's how those work. If you have a water in oil, how that works is that the skin just immediately absorbs the oil layer. Right? There are a lot of different ways that we can test to see if a lotion is oil in water or water in oil. So basically, when we look at this, if we have an oil in water generally conducts electricity. In contrast, a water in oil will not conduct electricity. Generally, there is very little fluorescence in an oil in water. Fluorescence just means it glows in a black light. That's it. So water and oil will fluoresce under a UV lamp. Okay. When you are testing for an oil in water, if you dilute it with oil, it will separate and form two phases. If you dilute it with water, it will stay in one phase. Okay, so if you mix it with water, it'll stay in one phase. Over here, if it's a water and oil, the opposite will happen. If you dilute it in oil, it will stay in one phase, right? If you dilute it in water, it will be, let me spell water correctly, it'll go into two phases, right? So the exact opposite there will happen. So these are some ways that we can test to see if we have an oil in water or a water and oil emulsion. And different lotions are different things. The other thing that you'll see that varies with your lotions a lot of times is the pH will vary. But it's not necessarily linked to oil and water or water and oil emulsion. So how are emulsions made? Right? So if oil and water don't mix, how do we get them to mix to make an emulsion? Well, the way that we do this is we add a surfactant. So the surfactant has a lipophilic group and a hydrophilic group. Lipophilic is just another word for nonpolar, right? Lipophilic just means it loves lipids, which are fats, okay? So we have a hydrophilic group, right? And we remember that loves water. Okay, so this is really similar. That surfactant, right? Remember, that's that same structure as the soaps that we were talking about before, right? So what happens here is you've got an oil, right? And a surfactant will come around and adhere to the oil and it'll form a micelle again, right? And then we mix it up and we disperse the micelle through in this stage, water, right? And it goes through the solubilization. And that solubilization happens when it becomes transparent. And the reason, interestingly enough, in the solubilized state, the micelle particles appear transparent because their diameter is shorter than the wavelength of light. And so that's why it becomes transparent there. So micelle particles become finer, they're transparent because their diameter is shorter than the wavelength of light. that's how emulsions are made, right? We mix some things and we make these emulsions. So what things do we mix together? Well, in moisturizers, lotions are mostly water. You want to use deionized water, right? So lotions, I'm going to say, are about 70% water. Deionized water just removes all the ions, right? So things like sodium, chlorine, things that we find in our tap water, basically. These basically, one of the reasons you want to remove the ions or other impurities is they can cause discoloration with aging. So we want deionized water with no ions in it. The next ingredient in a moisturizer is an emollient. Okay, now an emollient is any substance that soothes or softens the skin, right? So an example is fat and oils, right? So in a lotion, castor oil, so examples of this are things like castor oil, shea butter, sunflower oil. I've seen sesame oil. These are all emollients that we see through lotions. Sometimes you'll see cocoa. So I was trying to figure out where I wanted to go there. That's why there was a long pause. Sometimes you'll see cocoa butter, but shea butter tends to be a little bit better as an emollient than cocoa butter. And again, you'll also see some sesame seed oils are starting to come out on the market too. So you'll see different emollients, but basically they're just oils and kind of these butters. Okay. Now we have emulsifying agents, which can be referred to as emulsifiers. These are large molecules that contain both hydrophilic, water soluble, and lipophilic, which is another word for hydrophobic, oil soluble groups, right? The hydrophilic group, hydrogen bonds with water. The lipophilic group will have London forces towards the oils, right? Now, these cause a decrease in surface tension between the two phases. And a decrease in coalescence of the dispersed liquid. Okay, and this can affect the viscosity. Now, you can buy emulsifying agents. Examples of these include things like, if you look on your lotions, you'll see like cedarol alcohol. That's an emulsifying agent. Polysorbate 60. Right, so if you look at your lotion, you'll see those. If you see any PEGs, that's polyethylene glycol, like 150 stearate, right? Or stearate 20. These are all examples of emulsifying agents or emulsifying waxes, basically. And we can just buy those, right? So you can look at these retailers that sell the components to make lotions, and they'll have a whole section of emulsifying agents. And you can look at the ones that you like to use. Other things that we'll find is we have humectants. These just attract moisture from the air to itself, right? So these are things like glycerin, propylene glycol, or sorbitol, right? All of these, by the way, are short chain alcohols. So an alcohol just has an OH group. And basically the way these work is they hydrogen bond to water. Right? So that's how the humectant works. You also have to have a preservative, right? And this just is used to prevent the decomposition or fermentation of organic matter. And it helps with the shelf life, honestly. Some examples of this are, and you can just buy these. Germabin is a name of one that's an example that's used as a preservative. Grapefruit seed extract sometimes is used, but it's not super as great. With preservatives, you really want a commercial preservative, basically. Those generally tend to work really well. You just don't want to mess around with things growing in your lotions. If your lotions start to smell like crayons or the color changes, that's a really good indication that you've got something growing in your lotion and you really need to get rid of it, right? So on every bottle, there should be a shelf life, and you should be able to see that. You'll have thickeners. Thickeners affect the viscosity of the lotions, right? A really good example is stearic acid is a lot of times used as a thickener. So if you look at your lotions, you'll see stearic acid sometimes. That's used to thicken it. When we talk about making it thicker, that means it has a higher viscosity. So thicker means a higher viscosity. Okay. If it's thinner or it flows a little bit more, it's got a lower viscosity. And then finally, you're going to have pH adjusters. These are just things that change the pH. A really good example of this is citric acid. If you look on your ingredients of your lotion, you see citric acid. These are acidic, right? They are going to make the pH lower, right? But we can also have things that are basic. Triethanolamine, right, is one that will make your lotions basic, and that has a higher pH. There's a certain percentage of the population that's allergic to the triethylamine. So I don't love using it, just honestly. Borax is also something that can be added to lotion to make it basic as well. And just your preference for acidic or basic lotions just depends on your particular skin type and the natural pH of your skin. All right, so that for us ends module 3, where we talked about soaps and lotions, but also intermolecular forces, Vesper, those large chemical concepts. As always, if you have any questions, please feel free to pop by my office.